Hey there, smart coder, long time no see. Welcome back to the stream. Today we're gonna be solving yesterday's weekly contest. Here's the link. Let's spin this. All right. So let's get started. Question 1. The contents were relatively easy in my opinion. Yes, I agree. They weren't the hardest, but maybe we can learn a thing or two by going over my solutions and my explanations. So the first one, it's the first part, count prefix and suffix pairs 1. So they defined a Boolean function isPrefix and suffix with takes two strings, and yeah, whether string 1 is both a prefix and a suffix of string 2. So we have to count the number of pairs with pairs ij with I less than j, such that isPrefix and suffix is true. Alright, so and there are only 50 words, and the words are short. So this is an easy, we can get away with a brute force. We can go over all the pairs and check the condition and count, right? So let's write down the function, right? So is prefix and suffix, and in Python we have starts with and ends with. So luckily it's very easy to implement. Now we go over all the pairs. We're gonna count in res. So we want j to be greater than I, and if isPrefix and suffix, words of I, words of j, then we count it. Alright, so this should be good enough. So get the examples right and accepted. Cool, that was easy. Not a lot to add here. Let me share my submission. And yeah, remember that with Python you can always use the sum function. So we could do something like this in a more Pythonic kind of code. So we would sum 1 when we find one that satisfies the condition, and this should work as well. And it's kind of a one-liner, kind of, because we have that. I mean, we could replace that if we wanted to make it a one-liner, but I like it this way. So this is another solution. But yeah, so let's see. Then we're gonna see how to solve this faster in Q4, which is the second part. All right, so find the longest. So let's get to question 2. Find the length of the longest common prefix. So we're given 2 arrays with positive integers. And yes, so we have to interpret the integers as sequences of digits. And well, we have a prefix and a common prefix. we need to find the length of the longest common prefix between all pairs of integers such that this problem is screaming try it. Yes, that's how I solved it, and I had the same idea immediately. So return the longest common prefix. So yes, Smart Coder is saying we could use a try data structure and then to find the common prefix. So for example, if we have this right here, we have this example, right? We could create a try with the digits. So with our array 1, so yeah, I guess this is not very interesting, right? But because we're gonna have only here a 1, and so this represents a number 1. And then as a 0, and this is 10, and then another 0, and this is 100. So then and let's say that we have a 21 as well here. So in that case, we would have a 2, and then a 1, and here we would have 21, right? So, and then we go over each of the elements in array 2, and we go down the try, right? Here we have 1,000, so we go here, and we want to try to find the longest common prefix. So we go as low as we can. So we go here, 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 and we're done. So here we advance 3 times. So now the longest common prefix is 3, right? Which is between 100 and 1,000. So the code is pretty simple. So let me show you how I implement the try data structure in Python. So it's just a simple class, and here I think we don't need to do anything fancy. We just need so this is going to give us our next, so our child, and we need 10 elements, for one for each digit, right? And that's all we need. And we're gonna need a function to get us the digits for a number. So this is the standard. So this gives us the current digit, and we divide by 10, and then we have to reverse the result, because here we go from the least significant digit to the most significant, but we want the most significant digit first. That's how we are going to that's how the prefixes are defined in this problem. Okay, so then we have a function for adding a number to the try. So we go for every digit in the number, and we have our try. So if the next for this digit, so the child for digit D, if it's none, then we create a new node, and then we advance the pointer, the reference, and we don't need to do anything else here. And then we're gonna need another function so that that it's going to give us the longest prefix for the try. So this is going to be similar to this, but we don't want to create nodes. We don't want to add nodes. We want to, if we get to a digit where there's there's not another children, then we break, and every time we advance we count 1. So this is going to give us the longest common prefix. So now we create the try, and we go over all the elements we add all the elements in array 1 to the try, and then we want to go for every number in array of 2, and we're gonna get the longest common prefix here, and we want to get the maximum of this, right? Yes, the longest common prefix. So for each, we're gonna try with for all elements in array 2, and we get this right and accepted. Cool. Hey AK, how's it going? AKSR. All right, so this one's not a big deal. You need to know the try or tree data structure. Great, you're going good. All right, so here's my solution, my submission, in case you're interested. And let's move on to question number 3. Most frequent primes. So we're given a 2D matrix, and from every cell you can create numbers in the following way. So yes, you choose a direction out of 8 of the possible directions. Here they are enumerated, and then you keep appending digits. So for example, here you have 1, then you have 19, then you have 191, and you have to consider all these numbers and return the most frequent prime number greater than 10 out of all the numbers created by traversing the matrix, or -1 if no such prime number exists. If there are multiple prime numbers with the highest frequency, return the largest among them. Alright, so this is straightforward. We have to do the traversal as it is described, and then we just check if the number satisfy the condition, which is that it's greater than 10 and it is a prime. And then we just find the most frequent in the usual way. So we count the occurrences and we find the maximum. So we're gonna need a way to check quickly if a number is prime. So we notice that the numbers, so since the matrix is 6 by 6 at most, so the numbers are gonna have at most 6 digits. So we can have an upper bound of so we can do a sieve that's going to tell us quickly whether a number is prime or not. And so this should be big enough for all the numbers that we can have. Remember that we want to create the C before outside of the class. So because this is gonna be run only at the beginning for all the test cases, so we're gonna save time that way. So now we use the standard. So we create this table is prime. Initially we say that all of them are prime, and then if it's prime, yeah, let's say that is prime. I mean, we don't really need this, but let's do this for completeness. So these two are not prime. Then we start from 2, and if it is prime, we go over all the multiples, starting from the square, and we step p by p, and so this is a multiple of p, so it's not a prime, and we increment by 1, and now we know if a number is prime very quickly by just checking this table. So now let's do the traversal. So we want to know the size of the matrix, so that's gonna be useful. And so the starting, so let's first define the starting row and the starting column, and then let's define direction. So the delta of the column must be between -1 and 2 exclusive, and the same for the delta of the column. And we want to skip the case where they are both 0, because that's not gonna move. So we start from the starting row and column, and while we are inside of the matrix, we so we're gonna construct the number. Initially it is 0, so we add the digit, which is multiplying by 10 and adding the digit, the value here, and now we want to, now we want to check if cur satisfy the condition. If it's greater than 10 and is prime cur. If that's the case, we count it. So here we want to have a counter for all the numbers that we care about. Then we move on to the next element, and so on. So in the end, we're gonna have we want to get the maximum, right? So we want to get the maximum of what? Of the keys of the counter. So the keys are going to be the primes that we care about. And then here we want the prime. We want first to take into account the number of times that the primes occurs, and then the value, because we want to break ties based on the value of the prime. And we want to return -1 if there's none, if there's no prime. That's what we're told. So I think this should be it. And we get the examples right and accept it. Cool. So all running in one go. Yeah. I mean, yes, because we're thinking through the algorithm, so that's why things work on the first try. Okay, so now no compile errors. Yeah, let's just practice. So okay, so Q4. So Q4, I know. Okay, so this is the same as the Q1, but now we have longer. The array is up to 10 to the 5, and the length of the words are up to 10 to the 5. However, we're guaranteed that the sum of the lengths does not exceed 500,000. Okay, so one way of solving it, so there's been a theme lately in the contest that all Q4s can be solved by string hashing. So that's what I did for this one. So so how do we So I think there's another way of solving this using a trie data structure as well. But I think the rolling hash solution is simpler. So, I mean, it's not really a rolling hash because it's only growing. So that's why I say it's string hashing. So we want to go over the elements. So we want to go over the elements and considering the string 2, and we want to count how many string 1s there are. So strings 1s that are both a prefix or a suffix. So we're going to try all the prefixes and all the suffixes of our current string. So let's say that this is our string s. Right? So we have the string, so this is S0, S1, S2, and so on. And we want to compute a hash, a rolling hash that's going to be the same as it's going to be of this kind. So we need a mod. So let's call we need a mod number. A mod. So usually you use a prime number for the mod. So let's say that we use the typical 10 to the 9 plus 7, and then we want a base. Let's say that we use 101, which is just a prime number. You can try different values. You could potentially get collisions and get an error when hashing. But let's try these values. So the hash is going to be like this. So for example, if we have a hash of the first 3 elements, we're gonna have b to the 2nd power times an index of s of 0 plus b to the 1st and an index of s of 1 plus b to the 0 plus an index of s of 2, right? But the catch here is that when we want to expand the prefix to another value, to the next value, we want to do this in O of 1. We don't want to go over all the elements again because that would be too slow. So notice that if we get all these elements and we multiply them, and remember that this is all mod m, right? So if we multiply all these values by b, then notice that we're gonna have the hash for the first 4 values now. So because this is going to be now b to the 3 times this times b to the so this is going to be the same thing. Then now we have b to the 2 and then b to the 1, and then we add the new term, which is this. And so now just by multiplying a number and adding this new term, we got the next hash. So that's why this is fast. And then, but then we also want to do this for the suffix, right? And here the difference is that yeah, this is b to the 0. This is b to the 0, which is equal to 1. So that's why I didn't. You can omit it, right? So this is just 1. All right. Okay. Okay. So now we do the same from the other side, right? To get the hash of the suffix. But notice that here it is different, right? Because here, if we have, so let's call this, so this is s of n minus 1, s of n minus 2, s of n minus 3. The master's never wrong. No, believe me, I'm wrong many times. Anyway, so okay, so now we have s. No, sorry. So b to the 2nd times the index of s, and so when I say this is this function of I, I'm just saying that we have to translate. So we get a and we translate it to a number. Let's say it's 1, then b to 2, and so on. This is the function I that I'm referring to. So every letter maps to some number. And notice that I'm starting from 1. This is important, instead of 0, because if you use 0, then the hash of a, it's going to be 0, and the hash of a, it's also going to be 0. So you're going to have a collision for all the strings that have only a's. And that doesn't happen if you start from 1, I mean. Okay, so I was saying, so here we have the hash of the last 3, which would look like this. So here you have b to the 1 times s n minus 2, and then finally we have this. But notice that when we want to add this element, the next element going from right to left, we don't need to. This all stay the same. We only need to add the new term, which is going to be b to the 3 times I and sn to the minus 4, right? So we are only adding the biggest term here. So this is even easier. So once we have the 2 hashes of the prefix, we check if they are equal, because that's going to make them. That's the case where we found. No, the same as tail. No, because it's not reversed, right? So you want to see leet and leet for this to count. It's not reversed. If you want leet to be the No, I'm gonna do this hash. I'm gonna do the hash like I said here, going from right to left, and here going from left to right. The suffix formula, no, it's not different. It's so in this case, so you still want the hash to be the same as this, right? So here you want the biggest exponent on the L. So here you want exponent 3, then exponent 2, 1, and 0, and here you also want exponent 3, 2, 1, and 0, so that the hash is the same for leet and for leet. And that's why we have to do it in a different way when we go from right to left. Instead of multiplying and then adding the lowest term, we just add the highest term. And that is going to give us the hash in the same way. Okay, gotcha. All right, so let's see if we can implement this quickly. So our numbers are, so the mod we say is going to be this, and the base is going to be 101. So we're gonna count. Why the red thing? Oh, I think. Okay. So we're gonna count. We're gonna add to the counter all the words after we process them, so that we guarantee that if we find a prefix and suffix, it's to the left of the current string, right? Because that's what we are asked to do. So we go over each of the words. This is kind of a two-sum in a sense, where we have a hash table. I mean, it's a variant of wrapping carp in the sense that we're using string hashing, but we're not rolling the hash, we're only growing it, and we're doing it from left to right and from right to left at the same time. So we want to get the prefix hash and the suffix hash. Initially they are 0, and we're gonna go over the whole range of our current word S. And so the prefix, so this is what we wrote there. So the prefix, this is standard wrapping carp rolling hash type thing. So here the prefix we multiplied by p, as we said, well, not p, base, the base, and we add the index of s of I, and then we mod it, right? So this is going to update our prefix hash. Let's write the index function, and remember that we said that we wanted to start from 1, so we add 1. And then for the suffix, we want, like we said, we want to just add the highest term. So here we're going from right to left, so that means that we want the element from n minus 1 minus I, right? Because when I is 0, it's going to be n minus 1, and it's going to be decreasing from there, right? And we want to multiply this by the power of the base to the I, right? Because the first element has to be to the 0 when I is 0, so that's right. And we wanted mod, the mod, and we mod everything up. Yep, so this, now we have the two hashes. Now we want to know if they are the same, right? So that means that we found a prefix that is the same as the suffix, right? So if we found one, then we add to the result the count of how many times we've seen this word previously. That means to the left of S. So we add how many times we've seen that word, and now once we have process S, we add it to the words that we've seen. So we add 1, and this is it. It's pretty short, the code. So 420 and accepted. Right. So okay, this is the only part, and this is pretty standard. This is pretty standard rolling hash kind of calculation. So you should understand that part. Let me know if you want me to go over that again. I think I explained how when we go from left to right, how we grow the hash quickly by multiplying by b and then adding the lowest term. Since we're here, can you extend to Raven Carp? Would love to see you. How to shrink. Well, I mean, if you wanted to, so the standard Raven Carp. So here you multiply by the new term, so by S of I, and then you subtract by the term that is I minus some k, where k is the size of the window, right? And power to b to the k, and that is what you do to have a rolling window. When you go from left to right and you want to shift the window by keeping it size k. Yeah, Poe. This is Poe from Python, which already does mod. So yes, this is b to the k mod m. This is crucial for this kind of, because you don't want to do the power and then mod, because you can get a huge number. Yeah, it's very useful. It's very useful. You even can have, so if you do -1, you'll get the inverse, the multiplicative inverse. So it's very useful to have the power with a mod. So yeah, I think, did I share the link? Yes, the link to the solution. Yeah, I think I did. Okay, so yeah, so that's my take on the contest. So I couldn't take the contest. I absolved it. So when I absolved it, the Q4, the first 3 I did very, very fast, but Q4 I first went with the try solution, and I couldn't make it work. And then I realized that I could do the rolling hash, the hashing, string hashing solution. So I quickly changed the approach. But then after I solved it, I realized how to fix the prefix, the try solution. What made you try the try? No, I don't know. I think that's what. So when I explain this, I think it's very clear. Yeah, maybe I was a little biased because of the previous question, but yeah, I thought at the beginning of a rolling hash, and I couldn't immediately see it. So I think it would have been better to keep thinking about it a little bit more, and I would have saved time. Sandbox. No, I mean, sometimes that's good. I mean, and there is a solution. I think it's a little more complicated. I'm not gonna go over the try solution. But you can do it if you want to as homework. I think this is I'm really liking the string hashing code because it's very flexible. Complicated the shit out of the 4th problem. Yeah, you gotta think through it a little bit before diving into the code, because otherwise you could get lost. But yeah, I think the rolling hash is something that it's good to have it very intuitively studied, because it's very flexible, and it's been very productive in the last contests. All right, so that's all I have. So thank you for your support, and see you on the next one. I'm gonna be, like you've seen, I'm gonna be streaming more often. So is there a C function solution? Probably. I'm not very familiar with that, with the C function algorithm, or KMP. I mean, I've studied KMP before, but I think the string hashing algorithm, the Robin-Karp algorithm, as far as I know, it can do everything that the other algorithms do. So, and I think it's much easier to understand. So that's why I favor it as much as I can. Okay, so see you in the next one. Bye bye.